Hello everyone. Today I'm going to explain analog modulation. Modulation is a very important and core concept in communication, so I hope this video might help you later on. I'm going to use MATLAB in order to visualize the signals that we are going to talk about later on, and as well as the techniques. First, I'm going to go through some fundamentals, and then I'll go and explain uh, every single type of modulation that we have. First, we need to understand analog signals. Analog signals, let's say, compared to digital signals, which tend to be binary or in discrete form. In the contrary, analog signals are always continuous, and um, although sometimes limited in terms of value, it is continuous function, meaning that there is no holes. There is an infinite possibilities of values between -120 to 120 in this manner. If we think about the world around us, physical quantities are never binary or in discrete form. We tend to use units to describe them. Yet, their actual value is never of a discrete form. For example, you can call time as 3 minutes and 50 seconds, for example. You limited your measurements into seconds only, although you can go even smaller to nanoseconds and even further picoseconds and even further and further and further up to Planck's constant. Mathematically, we tend to think that there's an infinite possibilities of analog signals. Modulation is a process of modification of carrier signal with respect to message signal or modulating signal. And what that means is that if we have a carrier signal, simply a signal of a relatively high frequency that contains no information, and we have an information signal of a relatively lower frequency, and we would like to encode the process of encoding this information signal into the carrier is called modulation. We call the information signal a modulating signal, we call the carrier as it is, and then we call the resultant signal as modulated signal. So why do we have modulation? Modulation is a very important concept in communication, as I mentioned earlier. The reason behind that, to give you a better picture, let's think of human voice. Human voice is a very common type of information signal that we would like to send over radio waves, for example. Let's assume that the human voice is of 3 kilohertz frequency. Sending this message will require a huge amount of amplification to boost its power, because the signal itself doesn't have enough power to be transferred over, let's say, this distance, which also will influence the size of the antenna that we're speaking about. Let's say for 3 kilohertz, we would want to have something like a crazy 25 kilometer antenna to receive such signal. So in order to change that, we want to increase the frequency in general. So one way to do that is to have our carrier signal and then code our information signal into that. Another way is that if we have a control over the frequency of the signal that we send, we can use multiple frequencies over the same single media to transmit different data. Like, let's say your radio, when you tune in, you can tune into specific frequencies, and they're all sent to you over the same medium, which is basically air. So in order to understand how can we code this information signal into our carrier, we need to recall back that any given signal has 3 fundamental properties, which is amplitude, frequency, and phase, as you can see in this cosine signal. So we can variate one of these properties accordingly with our amplitude of the information signal that we want to send. And this way, we will code the resultant signal, the modulated signal, as we will have our modulated signal as a signal that conveys the message that we want to send. In amplitude modulation, as you can see here, the amplitude of the carrier signal varies accordingly with the amplitude of these message signal. The same thing goes here, but for frequency. So the frequency of the carrier varies accordingly with the amplitude of the given signal, and in phase, the phase is changed accordingly with the amplitude of the message. So let's start with amplitude modulation. In amplitude modulation, as I mentioned earlier, we have our amplitude of the signal itself, and then we have our carrier signal. Using modulation, both of them will result in this amplitude modulated signal, or the modulated signal here, where we have a higher frequency and the amplitude or the envelope of our signal is representing the amplitude variance of our signal. And in order to do that, simply, if we understand back here, assuming this is our carrier signal is a monotone cosine signal, we can then add our signal here into the amplitude of this carrier signal. So if you see here, if we are adding this EC represents the amplitude of the carrier signal, adding it into our own signal, the message signal, the VM, will ultimately result in a full AM modulated signal. This is what we call it, and then I'll go through the differences later on. What does that represent? But we call this a full AM signal. So let's go ahead and try that on MATLAB. To express our signals, we need to understand that simply there are two fundamental properties. One of them is the amplitude. So the amplitude of our modulating signal, let's assume it's 1. And then we have the amplitude of our carrier signal, let's assume it's 1 as well. So the reason I assume that they are equal is that there is something called modulation index, which will indicate how much percent of your signal is modulated. It's equals to AM divided by AC. It's always best and most efficient to have 100% modulation. With lower modulation, it still conveys our message, but not as clearly as in this diagram here. In this diagram here, I'm assuming that this one is almost 100% modulation. Of course, you would want to avoid the higher amplitude of your signal compared to your carrier signal, because in this way you will have an overmodulated signal, which means that some of your data will be overwritten. So let's go back here. Then we have our frequency of the signal itself, of the modulating signal. I'll assume it's 5 Hz, and then we have our carrier frequency, and this one has to be much more higher. Let's just think of it as 50 for now. Now let's write simply our equation. So if I am saying that our x, which is the modulating signal, is simply AM multiplied by cosine of 2 pi of the frequency of modulating frequency, and then I'm assuming that the carrier signal, XC, let's say, is AC, similar to this one actually. So we can just copy it. Where we have the amplitude is of the carrier signal and the frequency of the carrier frequency. We can then plot them together, but don't forget that this is only the frequency. This frequency has to be multiplied by time, by t, as in the equation here. Now, we need to understand something here. Computers in general are also digital devices, meaning that they don't really understand analog signals. So in MATLAB, you cannot just tell them to display your signal over an x-axis of time that is also continuous. What MATLAB can do, though, is get specific samples of time and then simply connect the dots. So we need to have a kind of sampling frequency for our graphs to appear. So I'm going to assume that my sampling frequency, there are specific rules about it, but A general rule of thumb is that it has to be at least double that of the carrier signal plus the bandwidth. And this one is called a rule of sampling. I'm going to assume that it's almost a 500. So a 500 sampling frequency. Then we can create our time axis. To do that, we will just like this, starting from 0 up to stepping by 1 over fs, the period of the sampling period, and then ending with 1. So this is a time axis for 1 second. And then we can later on display these two together. So to do that, I'm going to first indicate that this is figure 1. And then I'm going to subplot in order to display them together. Then I'm going to plot our x-axis has to be there first, so time, and then we have our x as our signal. And then I want to plot the carrier signal, the same thing, except here is xc, and then this one is 2. There we are. So as you can see here, we have our modulating signal and our carrier signal. Now, in order to do the modulation, we can just simply use the equation that we have earlier. So we can say that y is equal to AC plus x, all multiplied by cosine of 2 pi fc of t. And let's visualize that as well. So let's plot that. And then just paste here. We have our y. Oh, so this is very important. The multiplication in general in this MATLAB detects your variables as matrices. In this, of course, in this way here, it's a vector, not really a matrix, but you cannot just a simple asterisk indicates a matrix multiplication. This means that there has to be specific rules in terms of the rows, the number of columns and rows in order to perform this kind of multiplication. But we can add a dot here, and this way, this one is simply an element-wise multiplication, meaning that it's multiplying each element by each element, not really a matrix multiplication. So here we go. This is our signal here. So this is our modulating signal. This is our carrier signal. This is our modulated signal. As you can see here, the signal varies, the amplitude of, or the envelope of our modulated signal varies accordingly with the amplitude of our modulated signal. Now let's go ahead and try to see the frequencies contributing to this signal here. So in order to do that, we need to plot our frequency spectrum of this signal. And in order to do that, we can do a fast Fourier transform, an A50. So to do that, I will call my spectrum here as x1, and then I'm going to take the absolute in order to avoid negative numbers, and A50 shift to shift our frequencies closer to 0, and then use A50 for your fast Fourier transform into a y, or as our signal here, and then that should be it. And now we don't have a time axis to display this plot. Instead, we have a frequency axis. So in order to make that, we can just call it df, and then we have our sampling frequency divided by 2, of course, and we're stepping by 1, and we have our sampling frequency divided by 2 again. So this way we have a 500 ticks along our x-axis. In this case, it's basically the frequency axis. So let's go ahead and try to plot that. So I'll just call figure 2. Then I'm going to plot df and x1. So let's go ahead and run that. And here we go. This is our signal. So as you can see here, the amplitudes are very weird, and this is because we need to normalize our signal after the Fourier transform. So in order to do that, I'm going to divide by the length of y, and then multiply by 2. This one should give us a normalized signal. So we have here our amplitude. I'm going to focus only on the positive side for now. So here we have three bands. We have the carrier band here, and we have two side bands. So the carrier band, as you can see here, is at the carrier frequency of 50, and it has the amplitude of 1, which is AC. The side bands, on the other hand, has the amplitude of EM over 2, and they are existent at FC plus FM and FC minus FM. So 55 and 45. And that is actually not okay. And to explain further on this part here, we need to go through this. So we need to understand that here, all of the power transmitted is distributed among these three bands. So we have our AC here, which constitutes of 66.67% of the amplitude. This means that this carrier signal itself, the signal that doesn't have any information in it, uses 66.67% of the power used to transmit the signal, which is not okay. Our signal and our information is only located on the sidebands here. This means that simply 2/3 of the power is lost. So in order to counter that, what we devised is that, what if we thought of EC as the amplitude of the carrier signal as being 0? I understand that this is counterintuitive, but if you look here in this equation, we will have our information signal as our amplitude for the carrier, as simple as that. And this is called double sideband suppressed carrier amplitude modulation. This is not full AM. In full AM, we don't have a suppressed carrier; we have a full carrier. In this way, in this one we have a suppressed carrier. So this way, we only get two sidebands without the carrier, as you can see here. And each of the sidebands has the same amplitude, EM over 2, as you can see here, and existent on FC plus FM and FC minus FM. Now there is another way also to listen the power here. Of course, since all the power now, since we suppress this carrier, all the power is transmitted to the sidebands. In this way, we have 100% efficiency because all the power used is used to send information signals with information. Yet, the amount of power itself can still be reduced because these two sidebands are mirroring each other and they are extremely identical, meaning that this one and this one is simply the same. So we can get rid of one of them and then just use the other. Although the efficiency will be the same since all the power will be transferred to sidebands which will contain information, the signal components that has information. The amount of power is still lower by 50%. And also, besides that, one major advantage is the bandwidth. The lesser the bandwidth, the better, because now that you have, let's say for your FM radio, tuning into a specific frequency, meaning that you are listening to a specific media on a specific frequency, having multiple open slots, let's say for channels, means that it's more profitable for the organization and utilizing more of the bandwidth that there is. So in order to do that, we can take out one of the sidebands here, and we can use a low pass filter to do that. So after doing the equations, we will result with this final equation here. And in this equation, we can either do a plus or minus. If we're doing a plus, we will end up with the lower sideband of the two. And if we have if we use a minus, we will have the upper sideband of the two. And this will be simply our equation. Now let's try that in MATLAB. So to do that, let me close this first. So to do that, I can do the same thing. I can still write the equation again, but what I want to try here is a different approach. What we can do is we can use the MATLAB function itself for AM modulation, and it's called AM mod. And let's have a look at that. So in this equation takes three arguments, one of which is the signal, the carrier frequency, and the sampling frequency. In this function, the default carrier amplitude is 0. This means that this function implements a suppressed carrier modulation. So DSP SC as we want. So we can just use it in order to generate our signal, and we can try that. So we can say Y double. So this is a still double sideband, but with suppressed carrier. And then I pass my signal X. I pass my carrier frequency. I pass my sampling frequency. All right, and then we can plot that. So we can go ahead here, and then figure 3. Then we can plot this one with time. So now if we plot, just put a mistake here. So if we plot that, as you can see here, we have our modulated signal. As you can see here, this one is a single sideband, and to actually try that, this one is a double sideband suppressed carrier. And to try that, we can do the frequency spectrum we can plot the frequency spectrum of this signal. So to do that, we'll just do that, and then we call it x2. And then we can plot x2 here instead of x1. This way, as you can see here, we have our carrier suppressed indeed. And the two sidebands exist at +5 and -5 of the FC, and we have our amplitude as EM divided by 2. What we can do further is we want now to perform single sideband modulation. And in order to do that, there's also a function in MATLAB, and this one is called, let's call it Y single. This one is called SSB mod. So if you look at it, it takes the signal, the carrier frequency, and the sampling frequency, and it also can take another variable, another variable here, which is upper or lower. Our lower is by default. So in this one, we will have our lower sideband by default that is being modulated. If we want the upper one, we have to indicate that in the function. So you see here, it's sideband mod, and it should give us the lower sideband. And I'd like to plot that as well. Subplot of 2. And then here, this one is Y single. And then we can also have check the frequency spectrum of this one, find x3. Then But in this way, we don't need to multiply by 2 to normalize the signal. And you'll see here. So to do that, just call this one x3. So this one. So running this one, we'll have this. This is our signals here. This is the double sideband suppressed carrier. This one is the single sideband modulation. You might think it's not really modulated because of the looks of it, but the amplitude actually varies with time. Remember that the modulation index is only there when we have a carrier, but in this way we have to maintain a specific range of AM in order to get a better result in terms of more percentage of modulation. And as you can see here, this is the single sideband. This is the lower sideband because it exists as 45, and it's at 0.5, meaning that the amplitude is indeed EM over 2. So yeah, that's it for amplitude modulation, I think. Next, I'm going to explain frequency modulation. So for frequency modulation, we need to code our message signal into the frequency of our carrier signal. Simply, if our carrier signal, as mentioned, it is a simple cosine signal, we can add our message signal as a component of the frequency of this signal. So we are varying our frequency accordingly with the amplitude of our message signal. And to do that, we can simplify this equation furthermore by using the identity, and then we'll end up with this term here. This term is then simplified into this manner. We call the delta F the variance, the frequency variance of our signal. Here, as you can see, KF EM over W over omega M is then reduced to a single constant here is called beta, and this one is the modulation index for frequency modulated signals. And we can even expand this more using trigonometric identity, with cosine being multiplied into sine, with sine being the opposite of cosine here. And then that will result in two terms. We'll have our cosine of sine, and then we have our sine of sine. And then depending on the number of sidebands, we can then indicate every single one of them. Of course, in this manner, the number of sidebands is actually indicated. We can indicate it by using the Bessel table. In the Bessel table, the number of and the value and the value or the amplitude of the sidebands is dependent on the beta value, the modulation index. So let's try that out in MATLAB. So for this one here, by the way, the final equation, as you can see here, is called the wideband frequency modulation formula. There's also the narrowband, but for the narrowband, we assume that the beta has to be less than 0.2, and it has almost a similar equation. So let's go ahead and try them out here. So first, let me just comment these figures. And let's go ahead with our frequency modulation. So in order to perform frequency modulation, what we can do is we can plot our signal. Let's plot figure 4. And then let's subplot. Let's subplot our signal as it is before. So right here. Instead, we just don't have this part yet. So here we have our signal, and then we have our carrier signal. So how can we encode our signal, message signal, into the subplot, into the carrier signal, and we can do that using the following. So let's call this YFM. So we can actually use the formula here. So we can say that EC cosine EC or AC in this case cosine of omega CT plus beta sine omega MT. Actually, what we can do as well here, instead of writing the formula, there's actually a function in MATLAB that can utilize that, and it's called FM mod. Let's have a look at that. So for FM mod, we need to we will pass the signal, we pass the carrier frequency, we pass this the sampling frequency, but we also need to pass the frequency deviation of the modulated signal. This one is simply the delta F I mentioned here. So let's assume that our beta is equal to 2. According to the Bessel table, we will have 4 sidebands and 1 carrier band. This means that if this one is 2 and our FM is 5, we can then assume that our delta F, or the frequency deviation here, is of 10. So we go back here. We can say that we have our X, we have our FC, we have our FS, and then what we will add more is that we have the value of 10 as our frequency deviation. This way, we should be able to plot YFM, and it should be modulated. So as you can see here, this one is modulated, but I want to show you better. I think it's better to, you can see the difference if it is condensed in this manner. You can see that there is a specific compression here and release. This means that the frequency is varying. So here the frequency is high, and here the frequency is low, here the frequency is high, and here the frequency is low. And all of this is in accordance with the amplitude of our message signal. And hence, our frequency, our signal is frequency modulated. We can even go further, and let's try to plot the frequency spectrum of this signal. And to do that, just go through with this and multiply by 2 again. And what I'm going to do is that I'm going to do the Fourier transform of YFM, and I'm going to plot. I'm going to plot here X4. Oh, let's just call this one first. So we need to edit the subplots every time we want to add one. This is in terms of matrix, so we have 4 rows and 1 column. This one is X4, and this one is DF. And let's see ours. So as you can see here, let's zoom into the positive part. So we have this 4 distinctive sidebands and 1 carrier band, and this carrier band is of 50, as at 50 hertz, meaning that this is our carrier band at our carrier frequency. This is it for frequency modulation in general. So one last thing to discuss is the frequency modulation, is the phase modulation. And to be honest, the phase modulation is almost similar to the frequency modulation. Both of them are angle modulation, and at the end of the day, you will end up with modulating the angle part of our signal here. So, for example, here you can see that we can generate an FM using a PM modulator, and then we can generate a PM using an FM modulator by just embedding an integrator or a differentiator before the modulator itself. see here. This is the final form of the phase modulated signal, as you can see here. It's just that the phase represents our own message signal. That's all. I hope it was helpful for you. If you have any questions, please feel free to ask in the comments. I'll try my best to answer. Thank you very much.